am the head of the quantum software group at Cambridge Quantum Computing. Actually, I'm splitting my life in an 80-20 version between my university job up in Scotland, where I'm doing more theoretical things, especially working in category theory, and 80% at Cambridge, working on trying to get quantum computers to do something useful. Well, that's the theory, and the reality is more like this. So I recommend if anyone is thinking of doing a job split, try and find places that are less than 500 kilometers apart for the split. Now, Cambridge Quantum Computing is the company that I'm working for most of the time, and I want to talk to you a bit about mostly the ticket compiler, which is my main project. So we are in the UK, as you've seen on the map previously, and not in the suburbs of Boston, as some people think. But we do also have a small office in Berkeley. My colleague Mark Jackson is based there, so some of you may have met him. And also another small office in DC and another slightly larger one in Tokyo. So we're mostly working on quantum software at CQC. We are about 85 people in total, maybe a bit more now. But in Cambridge, where we are doing most of the quantum software, we're about 20, 25 people. And this is really where at Christmas time last year, obviously, since there are lots of people in the same room, this is not a recent photograph. And I'm not going to call out names as I go through my talk, but everything I'm going to tell you here is joint work with at least one or two of these people. I'll give citations for anyone that wants them towards the end. Okay, so what do we do? Oh no, before we do that, we work with lots of people. So obviously we've worked with LBL. We're also working with the National Physical Lab in the UK, the UK Quantum Computer Effort called NKIT. We have some projects with CERN. We're partners with most of the big companies who work in quantum computing, and I haven't written the names of any of the startups there, but a very large fraction of the startups in quantum computing as well. Lots of universities, the European Open Supercube project, and we have grants to pursue our own research projects from the British government. Now, what I said before, what do we actually do? We do quite a lot of things. So we have some people working in quantum random numbers, QKD, in machine learning, both quantum and classical. We have a small, very future-focused group, looking at doing natural language processing with quantum computers. But in my team, there's really two big topics, one of which is quantum chemistry, and the other one is development of this quantum compiler. So let's start with the chemistry. Now, I'm not a chemist, so you can ask me questions about chemistry and I will not answer them. Sorry about that in advance. So the chemists are working on a piece of software called Human, which is for quantum computational chemistry. So this is kind of the intersection of computational chemistry, quantum chemistry, and quantum computing. And they're working on a lot of fancy stuff, lots of variations on the theme of VQE and different kinds of molecular and solid state systems, lots of techniques for reducing the quantum computer resource requirements to do these things, lots of techniques for reducing the amount of error that you see in these kind of algorithms, and various techniques for scaling up from little tiny systems that you might be able to actually compute on your near-term IBM or whoever computer, and trying to apply that into much larger physical systems by combining different techniques in fancy ways. So if you want to ask some questions about this, it's very good if you ask them over text, and I can actually put you in touch with the chemists who are working on this. Alternatively, you could also ask Bert de Jonge, because he's talking to these guys pretty often about these kinds of things. Okay, so the chemists, they came up with all these great techniques, and then they hit this problem, which we all know as NISK, Noisy Intermediate Scale Quantum. Now, I'm assuming that everybody in this seminar is working in the area of quantum computing, so you know what I'm talking about here. So there is the famous paper of John Preskill where he introduces the term, but I'm going to just make it much shorter for you and say that noisy intermediate scale quantum stands for not many qubits and they suck. and I don't mean to like disparage the efforts of the people who are actually making these devices, because it's really incredible what's been achieved. But in terms of getting them to do useful computations, they are not very good. And so we have to start thinking about how to deal with that. So here's an old friend. I'm sure many of you have used this machine. This is it during its 14-qubit phase. And we can see a lot of detail about why this machine is not quite what people who are writing textbook algorithms back in the 90s were thinking of as a quantum computer. So we have a very limited set of gates, as you can see down in the bottom right-hand corner there. And so if I'm writing my algorithm for VQE, I should better use those gates. Of course, the qubits can't all talk to each other, so I can do CNOTs between pairs of qubits only as shown in the graph. And of course, they have to be oriented in the direction shown in the graph as well. So that's something else you should know about if you're writing an algorithm. And most damaging of all, the errors. And you can see from the error bars there that in the worst case, we're getting a CNOT error rate of about 10%. And some things which are not written in this display are the coherence times of the qubits, which are also pretty short. And that puts a hard limit on how many gates you can do before your state turns to mush. And we are not also seeing the errors which are happening at the whole system level, in particular crosstalk errors, which basically means when I try to do a CNOT in one place, that CNOT might be great, but it's making an error happen on some nearby qubits. So that's not even visible in this analysis. So if we want to actually get useful work out of these computers, we have to handle all of these limitations. And I don't really expect my friends in the chemistry department, when they're doing computational chemistry, to simultaneously be an expert in the exact kind of transistors that are in their MacBook. And I don't think it's reasonable to ask the computational chemists using quantum algorithms to be those kind of experts about the qubits they're using either, which is why we need something like a compiler. Yes, I have also this slide here suggesting that these textbook algorithms that you've probably learned about at the beginning of your education in quantum computing, they're not really thinking about the coherence times of anything. So you see, for example, the circuit for phase estimation. For each bit of precision I want in my answer, I'm basically doubling the circuit depth, which means that I just don't really have enough coherence to do these kinds of algorithms. And even if I'm working with, for example, an ion trap machine, which does have long coherence times, the number of gates is going up just as much as the depth, and the gates are still noisy. So this also isn't working, even if my nominal T1 time is unlimited. So what do algorithms for NISQ machines look like? They all look like this, basically. I've got some quantum circuit, which I'm going to execute many things. I'm going to estimate many quantities of the output state using different measurements. I'm going to combine them, store them all up in some classical optimizer, retune the parameters of my circuit, and go again until I hit a stable minimized value for my observable. Usually this is the energy, but it doesn't have to be. Okay, so that's what NISQ machines look like, and NISQ algorithms look like, which is where the main topic of my talk comes in. So CQC's main product is the software called Ticket. It is available for non-commercial use for free. So if you have your terminal open, you can just type pip install PyTicket, which is the Python bindings for it. And you will have the latest stable release. So Ticket is language and platform agnostic. So you can use a wide variety of input languages. It's retargetable, so you can run your job on many different computers. And it's designed specifically for NISQ devices and NISQ software. So in general, a modern compiler looks, not a modern compiler, an old-fashioned compiler looks like this. The programmer's source language, let's call it C, goes in one side, and then some machine language comes out the other side. And if we would go a little bit forward in time, we find that it's possible to decouple the source language from the center of the compiler, which we call the intermediate form, and that intermediate form can also be decoupled from the machine code which is generated. And this is what's used in all modern compilers, such as the LLVM. And so we have basically this core in the center which knows about the logical structure of the computation you're trying to do. And we have modular front ends and back ends that know about the source language that you're writing your program in, and also about the desired machine language that you want to actually execute the program. And that is the same approach that we've taken with Ticket. So we have a great number of possible input languages. Of course, Python is the biggest one. You can write your circuits directly in Python, but we support Chasm, Quill, Quipper. Q# is not ready yet, actually. That probably shouldn't be in the slide. And we have also an ongoing project to develop a new highly advanced functional programming language, a bit similar to the newer versions of Quipper, but with some different emphases, making it more suitable for NISK devices. And at the back, we support all the usual suspects of quantum devices you've probably heard of. Okay, so as a piece of software, it is a pretty high-performing C++ library, which is wrapped in Python. The modular parts, the front ends and the back ends, are pure Python. At the moment, none of this is open source, but we will be open sourcing the Python parts in the near future. So borrowing into it slightly more, we have this core PyTicket library, which is the thing that you will download if you type the command I suggested earlier. And then we have a lot of extension modules which provide support for the third-party platforms that we support. Now, for each of these platforms, the front end and the back end are quite separate. So if you wanted to use Circ to write your program in, but then you wanted to run it on Rigetti, that's something that you can do very easily with Ticket. And this list is not exhaustive, so we've recently added support for the AQT ion trap system. So AQT in this context means Alpine Quantum Technology. So this is the group based in Innsbruck. We have also a backend for the Microsoft world. You can use their simulator and their resource estimator, again, with whatever input program you want. The Quipper programming language, and a few other things which are either not ready enough or too NDA'd to talk about, but there are quite a few more things in the pipeline which will be coming out soon. Okay, so the general message is you use whatever you want to write the program, you feed it to Ticket, and then it'll run the program on whatever device you want. So we have inside that box a very powerful and pretty efficient optimizing circuit compiler. We are probably the best at circuit layout, which is this problem of mapping the gates in your desired circuit onto the places where you could actually do gates in your superconducting device. Because we're thinking about NISK algorithms, you can write your circuits with symbolic parameters, and the optimizer can still simplify the circuit without resolving the values of those parameters. And quite importantly, we do, where it's available, use calibration information about the device to improve the overall fidelity of what you're getting. And devices where that's not available, of course, we try to improve fidelity by just reducing the number of gates and the depth of the circuit. So here's what the Python interface looks like. You can see at the top, I'm loading in a circuit in Chasm format, and then I'm adding a couple of gates to it and say I want to measure all the qubits. Then I specify the machine that I want to run on. I check that it's allowed, that it's possible to run the circuit on that machine. And if it's not, then the compiler will attempt to compile it into a form which is good. And then I can use the methods at the bottom to send this circuit off for execution, run it 100 times in this example, and get some results back. And I just want to focus your attention on that line 5, which is the only place where I say what I want to run this on. So if I wanted to run it on a completely different computer or maybe a simulator, I would just change that line and everything else stays the same. The compiler will do the correct thing to make the circuit run well in your chosen device. Okay, so there's a lot of passes in this structure. So by pass, I just mean a particular transformation of the circuit. And I won't go into all the details of this. So most of the work is happening before we even know what device we're going to run it on. And then there is an architecture-aware phase to lay it out correctly, and then an architecture-aware cleanup phase, which does all the kinds of optimizations that will preserve the property of being able to run on the device you chose. The passes are actually modular, and they have their own core logic style type system that will allow you to combine them in a way that you want, but will enforce the property, for example, of being runnable on IBM. And so it's got this kind of correctness checking that stops you from writing circuits that can't be run. I mean, if you want to, this can be turned off. But the key point here is that when the front end generates some kind of initial attempt at a circuit, it's quite useful if the optimizer, the first layer of the optimizer, knows what was coming in. And this is where we try to be very helpful to our chemistry friends, because we know the kind of circuits that they like to generate in their algorithms. Which brings me to the first thing that I wanted to talk about. So this is some very recent work, and I'm just going to skim through it quickly because the paper isn't out yet. So I showed this picture earlier. So this is what the typical VQE algorithm looks like. And the quantum part looks like this. So I have some initial state. Maybe it's not all zeros. Maybe it's something simple like Hartree-Fock state, whatever. I go into parameterized ansatz and then I measure. Okay. So what do these ansatz typically look like? There's, broadly speaking, two classes. The ones which are physically motivated, like the unitary coupled cluster or adapt. And these have some nice properties, namely that they're probably going to converge. They've got some physical motivation behind their setup, and they're easier to reason about what's happening, what's the actual physical properties of the system you're trying to simulate. But the big demerit here is the circuits they produce are pretty deep. On the other hand, we have these hardware efficient ansatz, which are very shallow by design. That's really the only property that we expect for them. Their convergence might not be guaranteed. They suffer from a particularly nasty form of the barren plateau problem. And it's very difficult to use any kind of reasoning about the system you're trying to simulate with one of these ansatz because they have nothing to do with that system, right? You're just tuning the parameters and hoping that you can find the ground state. So as compiler people, these very shallow circuits, these hardware efficient ones, there's not a lot of room to improve these in terms of gate count or depth, because they're designed to be essentially incompressible. So we're going to focus our attention on the other side of the picture, the green one, the physically motivated ansatz, in particular, the UCC family of ansatz. So they all look like this, basically. So I have some initial state, usually Hartree-Fock state, and then I apply a unitary to that. And we can just ignore this part. The key here is that the unitary is made up of Pauli operators, which are exponentiated and summed. And so our strategy in very broad terms is to look at the terms in this summation and to sequence them in a particular way such that commuting sets of Paulis are found together. Because these sets are all mutually commuting, they're all simultaneously diagonalizable. So we do that. And then the resulting thing you get is actually a phase polynomial, or rather it's a bunch of single cubic Cliffords and then a phase polynomial and a bunch of single cubic Cliffords. And so then we can use some existing techniques to synthesize low depth circuits for these phase polynomials. And the trick here is really in finding clever ways to diagonalize these commuting sets. So I'm just going to show this one pair of charts. So what we have here is looking at the UCCST, So unitary coupled cluster singles and doubles and sets. The x-axis is the number of spin orbitals in the simulated system, which is a kind of physically motivated measure of how big the resulting circuit is. It's not interesting. It's not actually a reasonable metric to say what's the size of the circuit, because there is no circuit at the input of this problem, right? We have only this this expression given in terms of Pauli's. So the left chart is the number of C0 gates, and the right chart is the depth of the circuit where we only count the C0s. The reason we use this metric is because the error rates for single qubit gates are typically an order of magnitude less than the C0s. And so counting just the 2 qubit gates is a much more reasonable measure of cost for NISK circuits. Anyway, so the 3 lines on the chart, the green one is what you would get by taking standard ansatz generation method from, I think we used Qiskit in this chart. It might have been Open Fermion. And the blue line is the commuting set method of synthesizing the circuit. And it's a log scale, so you can see that we're getting a fairly substantial reduction compared to the naive version. As the legend says, this is using the Brahvi-Kitaia qubit encoding. This method is insensitive to the qubit encoding. It works for anything. So this is relatively inexpensive. The most expensive part of the algorithm is cubic in the number of qubits, which is not too bad. We're obtaining on average a 75% reduction in depth. And in the best case, we actually got 90% reduction in the depth. It works for any ansatz, which is coming from a trotterized operator. And it's not in PyTicket yet, but it should be very soon. In fact, maybe I'm lying. Maybe it is already in PyTicket. And the paper will be, I hope, on the archive next week, but I don't want to promise that. So more details of that will be available in the near future. Okay, so we generated a really low depth circuit, but we still haven't addressed this question of fitting the circuit into the computer. So for the uninitiated, this is what I call the routing problem. So here's a very small 5 qubit circuit. And if you look at the highlighted qubit, the 4th one, you can see that actually it requires interactions with all 4 of the other qubits. And if I look at the Melbourne device again, I can see there is no such qubit, right? I can't place that circuit in an unmodified form on this device. So the method, so this is what we call the routing problem. The question of how am I going to fit my circuit, which doesn't know about the device topology, onto the device. For some devices, in particular, certain designs of ion trap, this isn't really a consideration. But for superconductors, it's a major consideration. And for some ion traps where you have mobile ions, there's a variation of this problem, which is also pretty important. Okay, so generally speaking, I've got 2 things. I've got an input circuit, which is shown above, and I have a undirected graph, which I call the architecture, which says which qubits can talk to which other qubits. In principle, this could be a DAG, but I'm going to assume that I can reverse the direction of my gates, my 2 qubit gates, if I need to, for negligible cost. And the reason I make that assumption is because I'm already assuming that single qubit operations are negligible cost. Okay, and then what I have to do then is to, whenever I have a pair of qubits, which are not adjacent in this graph, I'll need to insert some swaps into my circuit in order to move the qubits, the logical qubits, around the physical qubits until they are adjacent. Okay, and typically this is kind of expensive because 3 C0s is the price of 1 swap. And if my coherence time only gives me around 100 2 qubit gates before I run out of time, that is a pretty hard constraint. So we really want to reduce the number of swaps. The combinatorial optimization problem in question is NP hard, and that's just to do it for one step, whereas we want to optimize across the entire runtime of the circuit. We know there's a lower bound, log n depth increase. So how well can we do this? So here's the actual problem. I'm going to take my original circuit and I have to produce three things, not just one thing. I need to first produce an assignment of my logical qubits to the physical qubits to start with, a modified version of the circuit, including some swaps, which will actually conform to the graph here. And then at the end, the final placement of the physical qubits on the, of the logical qubits on the physical qubits. Because there's no particular need that they have to be in the same place. And it's quite useful to enforce a particular final placement of qubits and work backwards from that. I'm telling you the simplified version of the problem here because perhaps I don't need to use swaps. I can use bridges or some other more complex circuits that enable me to shuttle the qubits. The easiest to express version.
I want to make sure that it's plugged into the computer. Okay, that was good to check.
So we did a lot of data on this. So actually this is slightly old now, these results I'm showing you, but we used a relatively large set of circuits. They're drawn from various benchmark sets, up to 16 qubits, up to 500,000 gates, two different architectures. So IBM Tokyo is quite highly connected. Average degree is 4, and the QX5 is the same shape as the Melbourne device that I showed you earlier. Okay, so we allowed a maximum of 1 hour of compute time because some of the systems we compared against are actually quite slow. Ticket can do this entire benchmark set in about 5 minutes on the machine listed here. So what do we see? So in the top left, it results of using Ticket with its default compilation pass and no constraints on the qubit connectivity. So the different compilers are different colors. So Ticket is green, Quill is brown, and Qiskit is purple or lilac. I'm not sure what color you would call that. And you can see that if I have full connectivity, I really can't do much. These circuits are already pretty well optimized, so the optimizer struggles to make any improvements. In the places where we have managed to reduce the depth, in some cases quite noticeably, this is on the subset of examples which were chemistry circuits, and they are generated by some ansatz which our optimizer knows about and can do a lot better than nothing on. But for the things which were chosen to be already hard to reduce, they're just hard to reduce. You can do something, but not much. Okay, so then we tried the same set on 3 different devices. So the Rigetti Aspen, which is a fairly low connectivity device, about degree 2 on average. IBM's Rochester, which is similar degree of connectivity, and the Google Sycamore, which is a square lattice. So almost every qubit has degree 4 in this grid. And you can see that this heuristic method, which Ticket is using, is on average substantially better than the competition. But notice that the axis is not the same here. I had like 1 at the top of this one. Of course, when I'm inserting gates, I'm always making the circuit bigger. And so we can see that the Rochester architecture, if I look at Qiskit, it's blowing up the circuit size by about a factor between 3 and 4 usually, whereas Ticket is between 1 and 2. And for the highly connected Sycamore, you can see that we're actually best on this high degree graph, and we're blowing that up by about a factor of 2. Okay, so these results are a bit old, so I think everyone that I've showed there is doing better, but in particular, we have improved our routing since that paper was shown. But due to the expense of actually running these benchmarks, we don't rerun them too often. There's one thing about devices that I didn't talk about so far, which is the fact that we know the error rates. I don't necessarily care about the circuit depth. I care about the fidelity of the computation that I'm doing. So we have a recent paper in collaboration with some IBM colleagues looking at different ways of benchmarking real devices, which I will not show any results from today, but you can ask me about it later if you want to. But if we know that we have, for example, this map of error rates, can we improve the results of our circuit by using this information? And the answer is yes, we can. So here is 3 different methods that we have in Ticket. So the top one is just do nothing. It's a fairly naive placement algorithm, which is, I think again, maybe it's from Qiskit. The brown line is what we call graph placement, which is Ticket's default placement method, which doesn't use fidelity information from the device. And the lilac line is noise-aware graph placement, which does use fidelity information. And you can see here on the y-axis, the number of gates in the circuit. This is for an 8-qubit system. And on the x-axis, the number of gates. And on the y-axis here, this is the Jensen-Shannon divergence for the circuit that we're running in comparison to its ideal simulated output distribution. So if the distance was 0, they would be identical. So as we would expect, as the number of gates goes up, the divergence increases. But by using the noise awareness in the placement, we can improve quite a lot. So at 80 gates noise aware, we're in the same ballpark as 40 gates without the noise awareness. Okay, now that's routing. So routing works, as I showed before, by starting with a circuit and then trying to lay it out on the grid of the machine. And that is so 2019. We're like, that's old hat. We're done with that now. The new thing, the new hotness, is not to generate the circuit until you know what the layout's going to be. So as I mentioned in the first part of this presentation, when we're generating circuits for these chemistry Ansätze, the end result is a phase polynomial, which we then transform into a circuit using a method we just stole from Matthew Amy. So that's why should we not add the knowledge of the architecture into the mix at that point when we don't even have a circuit yet? And so that's what we call architecture-aware synthesis. So Ticket supports a large number of what I call higher level operations, which are like kind of macro objects, which are not gates, but they can be synthesized into circuits. And these objects, for example, are phase polynomials or terms in the ZX calculus or Clifford tableaus and things like this. And there isn't any particular need to think of them as circuits until you really want to execute them. So this is some recent work, which was mostly carried out by Ariane Meyer, who was an intern with us up until about a month ago. And she's gone to Helsinki to do a PhD. Okay, so I'll show you what we're talking about. So a phase polynomial, for anyone that doesn't know, is an expression of this form. So it's a sum of a phase and just an angle times a linear Boolean function. And we call these functions parities, but that's not going to be very important for what I have to say. And then the function is acting on n Boolean variables. And those n variables will correspond to the n qubits in the circuit. And so the theorem is that if we have a circuit which consists only of C0 gates and Z rotations around an arbitrary angle, so not Pauli's, but any angle of Z rotation, then it computes the entry, which has the form of e to the I phase polynomial times, and then some reversible linear function of the basis states. Okay, and perhaps more importantly, the converse is also true. So every phase polynomial can be realized by a circuit of that gate set. And most importantly of all, that circuit is not unique. So if I have a phase polynomial, I have a lot of choices about how to realize it. Okay, so we didn't invent this. The algorithm that I know earliest of it, which I don't know if it actually is the earliest, is one of Matthew Amy from 2017, which is called GraySynth. And so this generates very low gates for phase polynomials, but GraySynth is not architecture aware. So that's not really suitable for what we're talking about here. That is what we used in the method I described earlier, but that's without restriction of qubit connectivity. There is an architecture aware generalization of it written by Beatrix Nash and various co-authors, who I don't remember right now. And this method has been implemented in Stack. So we have a new algorithm, which I'm not going to show you, but you can find the details of it in the archive link shown there on the slide, because the algorithm is kind of complicated. But basically, it's about using the fact that you can present a phase polynomial as a binary matrix and then do Gaussian elimination on it in order to generate the circuit. Now, the order in which you do things is the key to making sure that you actually are minimizing the depth. So what do we see? I think the architecture that I'm using here is a Rigetti one, but these are randomly generated phase gadgets, which is phase polynomials, same thing. And we are seeing here the normal ticket, where I just synthesize the circuit and then try and route it, is the orange trace. And we can see that, you know, at low depth, ticket does pretty good because it's very good at doing that initial placement. But as the circuit gets deeper, it doesn't know enough about the macrostructure to do a good job. So it falls behind these specialized methods which know about the thing they're synthesizing. And you can see that the proposed method is scaling up to about the same as the Stack Steiner GraySynth method at higher numbers of gadgets. But if we just look at the depth of the circuit, we see that our proposed method is actually doing a bit better. So for the superconducting devices in particular, it's quite useful to be able to do low depth circuits because you're always fighting against your coherence time. And if my circuit designer has put my gates in parallel, at least gives me the option to reorder them in order to minimize crosstalk. Whereas if they're in a fixed ladder arrangement, then I might not have that flexibility. So I think the depth is the more important of the two metrics here. Incidentally, this method is not implemented in Ticket because we found a better way of doing it. So the paper describing that will be out sometime after the other paper, which I promised you at the beginning of the talk. But you can read about this method just now, that it was accepted at QPL earlier this year. Okay, so what are we doing in the future? So our objective as a company is to try to have our software work on every quantum computer there is. So we'll be supporting more architectures and more different technologies. So at the moment, we have ion traps and we have superconductors. We are looking towards optical and cold atom systems, hopefully this year, and perhaps even semiconductors in the further future. Now, everything I've told you here so far is gate level stuff. But we know, if you've been watching the work coming out of Chicago in particular, from Fred Chung's group, then you can do a lot if you give up on the gate model and go lower into like direct pulse level optimization. So that's on our roadmap to go down, but also we're thinking about up, because having knowledge of this higher level structure is very, very helpful in generating better circuits, as we've seen from the UCC example earlier. And so we're trying to find which high level primitives are actually most useful to application level programmers like our chemistry friends, but which also give us lots of options for how we synthesize them. And by combining this flexibility of synthesis with architecture knowledge, we should be able to do a lot better in terms of depth. Since we want people to actually use this, we're also working on better programming tools. And I think I mentioned at the beginning, we're designing a new programming language. And the major topic of work at the moment is looking at better ways of analyzing and suppressing noise in real-estate devices. Because that, even with all the best circuit optimization in the world, it's really not enough at the moment with the levels of fidelity we see in current day machines. And of course, if we're going to be generalizing further, we're going to be looking at new models like measurement-based quantum computing, which is particularly relevant to the optical world, but can also have some benefits for superconductors, especially if you can control the amount of post-selection that you're going to do. Okay, so I think I've just about reached the end of my material. So I want to remind you all to pip install PyTicket and try out the software. Let us know how it's working for you. And before I wrap up, I would like to end with an advert for something not really related. The Quantum Week of Fun was originally planned to be happening in Cambridge in the end of September. It's now going to be fully online because you might have heard about this coronavirus plague that's going around, which has made having actual in-person conferences a bit impractical. So the Quantum Week of Fun is actually 4 separate workshops. The International Workshop on Quantum Compilers. So that one is having as invited speakers some people who may be known to you, Eleanor Riefel and Margaret Martinosi. There's also a 1.5-day workshop on quantum computational chemistry, a day-long workshop on quantum algorithms, and another day-long workshop on natural language processing. And we're going to do our best to try and schedule things so that you guys in California can watch some of the talks live at least, and everything else will be recorded for later viewing. So please do take part in the workshop, send us a paper, give us a talk. And with that, I want to say thanks for your attention, and I'm happy to take any questions you may have.
All right, thank you, Ross. So virtual applause or noisy applause. I feel a lot better now. Actually, I felt good before about using Ticket directly for AQT, so you can add AQT to the list of supported devices. And questions, please. We have 10 more minutes, looks like.
So let me ask a question. This is Al from Argonne. The noise model that you talked about with sort of gate fidelities, I mean, it's obviously useful, but it seems fairly crude. Have you found that there's utility in using more sophisticated models of the noise on the devices?
Yeah, it's a topic we're actively investigating. I mean, as I mentioned when I was talking about the Melbourne machine at the start, you can't see crosstalk in this model at all, which is actually much worse than the gate level noise. So we are looking into ways to analyze that and to try to mitigate it. I don't really have any results to report to you at this time.
Well, if I can make a parenthesis here, so we also looked a little bit at that. One reason is because the devices have so limited connectivity. Even if you know the noise information, turns out there aren't many things you can do. There aren't many possible placements. That's one of the problems. If you have a richer connectivity, probably this is going to be actually very useful, the the noise-aware placement?
Yeah, I mean, you can do a bit, but if you're actually using all of the qubits in the device, then there is limits to what you can do. Say doing crosstalk aware placement seems to be a bit more promising, but then also there's an element of scheduling that you have to do as well in that case. I hope that if you invite me back this time next year to have some results on this one, but we don't have anything done just yet.
Okay, thanks.
Russ, you talked a little bit about architecture-aware synthesis. How do you see this playing out in the design of languages for quantum computers in the future? Do you imagine that compilers are just going to have a whole bunch of intrinsics built into them in terms of algorithms, or are we going to have to rethink what algorithm design is going to look like for these quantum computers? What are your opinions on that?
So we are coming to it from a very narrow perspective, which is that everything that you can do with a quantum computer in the near future is going to basically look like a VQE kind of problem. Modulo some details of the ansatz or things like this. And with this in mind, then the thing that we are thinking about is, yeah, as you said, lots of intrinsics, I think is a good way to phrase it. Like, what are the building blocks of the wave function that you're trying to arrive at? What are the building blocks of the Hamiltonian you're trying to simulate? And then think of clever ways to construct those things. I have limited hopes for general purpose quantum programming in the very near future. And the only thing which I think has lots of potential in that kind of direction is looking at things which are more like MBQC, where you want to go from something which is essentially sequential in nature and turn it into a graph state and manage the execution in parallel. I think that's a very interesting problem, which is on the horizon for things which people will actually be able to do pretty soon. I'm not sure if I really answered that question or not.
Yeah, no, that's great. Thanks.
So I have a question. So one of your slides, I think, was saying you guys are looking at the typed language. Are you looking at the qubits and qubits, or hybrids, or hybrid multi-level systems programming at all? If it makes any sense.
So this line of work is coming more from my academic world, where I share an office with a bunch of people who are programming language theorists. And the kinds of things they mean when they talk about types are, well, in particular, dependent linear types, which is some level of abstraction above qubits, qtrits, and so on. So that's not something that we're really thinking about at the moment. But it is something which is interesting to think about. And in particular, there's some interesting work coming from the ZX community, where they are looking at arbitrary dimension versions of ZX calculus and how to jump between the dimensions. So it becomes more like a general tensor network programming system, but like a tensor network where the dynamics are somehow algebra rather than actual dynamics. I'm not sure that I'm making much sense here. So the language that we're thinking of for developing is more to allow people to write correct programs in the way that strongly typed languages are usually being thought of, where the type system is essentially a theorem prover, that it makes it impossible for you to accidentally reuse a qubit, for example. That's a very boring example, but it's quite an important programming error.
Okay, thank you.
I had a question about, you said that this TCAT kind of takes any language, any input language, and then can transfer it to anything on the output. A lot of these hardware platforms you mentioned, they have a native language already, like Quill for the Rigetti systems. Does TCAT take any of the input languages and then convert them to an appropriate like native language to be run, or how does it run on the actual hardware?
It depends very much what the device provider has made available. So in almost every case, there is some way of specifying a circuit as a bit of JSON or as a CASM file or something like this, which you can transmit to them. In this particular case of Rigetti, I don't remember if it's necessary to send them a Quill object or whether we can go lower through their API. But in general, we are using the lowest level thing that's available in the API.
So
Great, thanks.
we had a internal discussion. So for AQT, the portability layer is CAS. But for example, I think we had an internal discussion whether the internal representation is called Qtrl. We had a discussion if you want to go from Qtrl to CAS and then use optimizing compilers and TCAT and then go back. And I think we decided against. And we assume that everybody's going to go to CAS.
Yeah, well, CASM is absolute. I mean, if you just want to like specify a circuit, well, it's not even that good. But if you want to have any kind of classical control in your program, it's just garbage. I mean, Quill is much better. There are various extensions of CASM which are more suitable, where you might be able to write some simple Boolean conditions directly in it. But I think CASM is ripe for replacement, and I would like there to be one replacement and not everyone making their own version. So I think
in our case, it was. Oh, sorry. Go on.
I mean, this is more pertinent for the ion trap world, where it's kind of reasonable to do classical computing during your quantum computing. If you're in a very fast coherence time setup, we need to compute everything in advance, then it's less of an issue. But for some platforms, I can indeed measure a qubit, look at the answer, and then decide what gate I want to do next. And in that kind of situation, CASM is not an adequate language.
Yeah. In our case, it was a lot more pragmatic decision. We didn't have enough input circuits to translate, so it wasn't worth it.
Mm-hmm. Yeah, so one of the ongoing projects that we're trying to get off the ground at the moment is to design a virtual machine, which would be a kind of generalized model of quantum computer that could accommodate all these different actual machines and serve as a common target for different languages. Because there's quite a lot of variation between, in particular, the interaction of the classical and the quantum parts of the computation. So obviously we have this big classical loop on the outside, but in many machines, there's also the possibility to do very fast classical stuff on the inside as well, which would have completely different real-time constraints. Trying to get a handle on all these things in a unified manner would be quite useful if you're somebody like us who's making a retargetable compiler.
Excuse me. Just now, you mentioned about the measurement-based quantum computing. I want to know how complex that measurement-based computing is going to be. You will foreseeing in maybe in the next year or two. So, based on the measurement and then derive the next something, how complex that computation is going to be?
So this is slightly related to my previous answer as well. So my working assumption is that I'm going to have more qubits before I have better qubits. In that case, it makes sense, in particular if the measurement fidelity is not too bad in the devices. It makes sense to trade width for depth and try to do everything as measurement-based computation. So I don't think that the complexity is daunting. I mean, if you think of a quantum circuit as a tensor network, then the number of nodes in this network would be roughly constant. Just some of them will be physical qubits, and we'll construct a graph state to use it, and some of them will be operations happening to qubits which are extended in time. From the software point of view, there is really no difference. Like one of the concepts in the ZX calculus is that we don't care what order is time, and it makes it easy from the software side to swap from a measurement-based computation to a circuit-based computation and back again. No problem on that side. It gets more interesting when you think about some of the technology for generating graph states, which is usually lossy and heralded. So you have to keep track of which graph state you actually made, and then do some classical compute to work out what you're going to do next in your process of building the graph state you actually wanted. Now, that's pretty interesting. And I think that is the hard part of doing measurement-based computing for real. But if you're doing it on, I don't know, for example, this 72 qubits crystal cone that Google used to talk about, then again, your big bottleneck there is how good are your measurements. And if the measurements are good, the measurements are better than 2 qubit gates, then it's kind of a sensible thing to do to translate circuits on a smaller number of qubits into MBQC on a larger number.
Okay.
Any more questions? Looks like we are close to the time. Okay, if nobody speaks, I have one more. Are you guys doing anything about debugging? Do you have any support? No?
It depends
Know
on
of anybody?
the program you're running is a Python program. So, okay, I should take that back. The whole point of having a dependently typed programming language is to make it harder to write buggy programs. But there isn't any way that I can think of that you can reasonably debug a quantum program of realistic scale. So, yeah, we're not working on it.
Okay, all right, okay. Any more questions? And let's thank the speaker again. Thank you.
Thank you.
Hey, it's 12.